All right. Very interesting new part. Close the books. Focus on this. Relationship between electric field intensity and potential gradient, electric field intensity and potential gradient. The relationship between electric field intensity and potential gradient. Relationship between electric field intensity and potential gradient. Potential curve, we have drawn this, and more clearly, we know the relationship is what? Potential gradient. Right? Potential gradient. So what is this shape? Rectangular hyperbola. Hyperbolic shape, rectangular hyperbola. Right? So rectangular hyperbola, V proportional to 1 over R. So let's go to the curve and we mark the point. We mark the point and draw the tangent. Right? Draw the tangent and point the V value here and go to the other side. This is the R value. Now we are trying to find the gradient. How do we find the gradient? How do we find the gradient? Tell me. How do you find the gradient? Delta V only. So we need delta V. So we have to go to the left delta R amount. We go to the left delta R amount, that is called R1. And the corresponding V coordinate is V1. Go to the right delta R amount, that is R2. And the corresponding Y coordinate is V2. අත හොදන් එන්න ගිහිල්ලා ජනිල දාද ගෲප් එකේ දාන එක බලන්නකෝ ඊට පස්සේ හවසට මොකද වෙන්නේ කියලා. So this is delta V, this is delta R. Now we can easily mark what? Easily mark what? Tell me. Easily mark what? The gradient. So how do you get it? V1 minus V2 over V1 minus V2 over R1 minus R2 or V2 minus V1 or V2 minus V1 over R2 minus R1. So either of it. And at a glance you can see R2 bigger than R1. Why? R2 is R plus delta R. R1 is what? Sorry? R minus delta R. Right? For a point charge, we know that V1 is Q over 4 pi epsilon R1. Right? Point 2, V2 equals 1 over 4 pi epsilon Q over R2. So we can write them. Is that clear? So since R2 bigger than R1, definitely V2 smaller than V1. Now we are going to substitute this to the main expression. Substitute this to the main expression. Substitute this to the main expression. Q over 4 pi epsilon R2, Q over 4 pi epsilon R1. Right? R2 minus R1. Now, Q over 4 pi epsilon common taken out. 1 over R2 minus 1 over R1 over R2 minus R1. This derivation is not in the syllabus, but we are deriving it for you to prove the fact. So I take the common denominator for the numerator. Numerator 1 over R2 minus 1 over R1. I take the common denominator R1, R2. Right? Here at the top you can see R1 minus R2. I will take it separately out. I will take it separately out. Take separately out. So 1 over R1 minus 1 over R2. Sorry, R2 minus R1. That's how we started, right? Just go to the slide. Slide, yeah, R2, right, okay. Over R2 minus R1. So this is the calculation for bio students. R1, R2 over R1 minus R2 over R2 minus R1. So this is the denominator of a numerator. So it is coming down. So R1 minus R2 over R2 minus R1 over 1 R1 R2. Right? Okay. R1 smaller than R2, I can take minus sign out, R1 minus R2 over R2 minus R1 over R2 minus R1. That part is cancelled, and what is remaining? R1, R2. Is that clear? But on the other hand, we know that. But on the other hand, we know that part R1 my R1 R2 product. Now this product that we can write R1 as what? R minus delta R. R2 is R plus delta R. Now what is this component? R minus delta R into R plus delta R. What is it? Sorry, R squared minus delta R squared. R squared minus delta R squared. But delta R is very small value. So you ignore the value and 1 over R squared. When you see 1 over R squared, what is this there in the right hand side? Q over 4 pi epsilon R squared. What is it? Electric field intensity. Electric field intensity. So we can say electric field intensity is potential gradient. Is this clear? Right? Okay. So we introduce another unit for electric field intensity. Already we had a unit, Newton per Coulomb. Newton per Coulomb. Right? Newton per Coulomb. Okay? Now we have a unit called volt per meter. Volt per meter. So E equals delta V over delta R. E equals delta V over delta R. We'll leave it there and you go through it, and when we go for the special part of developing the potential distance graph based on what? Electric field intensity distance graph, right? Quickly copy that. Okay. So what does this mean? We come to the board again, and now what does this mean? Like, there is no electric field. What does it mean? Concept, another good concept. There is no electric field intensity, there is no field. What does it mean? Interesting. Delta V over R equals 0. Is that clear? What is mean by that? Delta V equals 0. What does it mean? No potential difference. No potential difference means what? Potentials are equal. So we call it equipotential surface. We call it equipotential surface. Right? That is the next part of it. So you have the screen there. So conducting sphere behaving as an equipotential surface, even though we call it a surface, that is not a surface, it's the entire body, entire object is an equipotential surface. Where I'm heading towards, the first derivation we did, example 2, solid conducting sphere. The solid conducting sphere, entire sphere, the body internally center to the outer surface, everything is what? An equipotential surface. So equipotential surface is a Gaussian surface. So now we are going to handle this one. This is the second graph we drew today. This is the second graph we drew today, right? So when we consider the second graph, you can see the center of the metallic or conducting sphere is producing no electric field intensity at the center, right? So what does it mean? Inside it, potential is the same. What is the potential? Q over 4 pi epsilon R. So that's how the graph is. I repeat this. I go back and forth. Electric field intensity graph. Electric field intensity graph is what? No electric field intensity at the center. Potential graph, the same potential. Same potential. So similarly, we can get the idea, very complicated one, but this was given as 2010 MCQ, unfortunately, okay? This one. So we have drawn this, right? Can remember, we drew this. This is for what kind of sphere this is? Huh? Insulating sphere. So when you look at the insulating sphere, you can see there is an electric field at the center. If you take one part of it, C, to the surface, for the positive side, you can see there is a y equals mx type of a curve. Y equals mx type of a curve. Right? So y equals mx type of a curve. Inside the sphere, you can see the gradient is, interestingly, gradient is increasing, electric field intensity increasing positively. Right? Now this is interesting. This is complicated. Thinking must be very seriously needed here. Why? Because E increases. You have to think reverse. Now, E equals delta V over R negative. So, E is increasing positively. E is increasing positively, right? So delta V over R negative. So this is increasing positively, this is decreasing value wise. Value increases, negatively increasing. So you may have a problem like -2, -3, -5. Now you can see the negative value, not the number comparison. Huh? Why? Negative sign is the direction implication. So the gradient increases negatively. Value increases positively, gradient increases negatively. So how do you draw a negatively increasing gradient? Negatively increasing gradient. How do you do negatively increasing gradient? Can you remember? Unit number 1, graphical analysis. Unit number 2, I explain how do you mark negatively increasing gradient. Explain. Negatively increasing gradient, inside it negatively increasing gradient. So we'll go for a better diagram on the screen. Better diagram on the screen, right? So you can see negatively increasing gradient inside, to both sides, to the left as well as to the right. Okay, so that's how we explain. This was given as MCQ in A-level paper, 49th or 50th MCQ in 2010 or 2011, if I'm not mistaken, 2010. Okay, right. Explain the full idea. Now go through that one, both graphs one more time for the conducting sphere and non-conducting sphere. gradient. Yeah, this is like E, backward, E positively increasing. E positively increasing means what? V negatively increasing. Inside the sphere, E is a linear positive increase. This is positively increasing. Therefore, the gradient of EVR graph is method. Thank you very much. Typo එකක් තියෙනවා මෙතන. Thank you. The last line, negatively increasing. VR, potential distance graph is what? Negatively increasing. Negatively increasing. It is negatively increasing. ඒකේ තාමත් ඒක තියෙනවා. ඒක තව typo එකක් ආවා ඒ පාර. Right, negatively increasing. Laptop එක චුට්ටක් කචල්. So this is the presentation laptop. We have to change that one soon. Right, okay. Right, gradient is negatively increasing. Gradient of the graph negatively increasing. Negatively increasing gradient is this. Right? Right? Okay. So that is correct. Thank you very much. There was a typo at the bottom. That is negatively increasing graph. Gradient is negatively increasing. Correct it in the note as well. Thank you. Right. The electric field intensity variation out of the sphere is the electric field intensity of the usual charged conducting sphere as well as the field intensity of the point charge. But inside the sphere, it varies linearly from the center to the surface. Potential gradient, yes. Okay, so we go to another one. Can you remember this one? Can you remember this one? Can you remember this one? Yes, what is it? What is it? Okay. It is called uniform electric field. Why? All field lines are parallel. All field lines are parallel. The gap between the field lines are parallel. No change of the gaps. So this is called uniform electric field. And the intensity is constant. Intensity is a constant. Is that clear? Intensity constant. Now, inside no intensity, after that constant. Now we'll go backwards. Right. So intensity constant, inside that, this is the idea. This is a little bit hypothetical, you can see that. This is the idea. The inside the conductor, it is a equipotential again because it's a conductor. After that, potential drops uniformly. Right? The potential gradient is constant. So the gradient of potential distance graph is a negative constant gradient, right? Okay, we'll give the exercise I promised. This was given in 2007 or 9. Hope you all attempted them. Now close the books, textbook. I'm going to check whether you studied during that extra 30 minutes you got after the break. Chamat? Yes. After watching the match, did you do the work? Match එක බලන එක නැවැත්තුවා. Right, very good. අද නේද ශ්‍රී ලාංකීය ජාතියක් වශයෙන් අපිට හරි අභිමානවත් දවසක්. ඇයි? ඔව් ඕමානය වගේ දගන්ත ක්‍රිකට් රටකට ලකුණු 100කින් අපි ජයග්‍රහණය කළා තියෙනවා. ඒ අනුව කුසල් මෙන්ඩිස්, දසුන් ශානක වැනි ක්‍රීඩකීන් තවත් වර්ල්ඩ් කප් එකක් ක්‍රීඩා කිරීමට සුදුසුකම් ලබාගෙන තිබෙනවා. අපි දිගටම මැච් බලමු. Right? Okay. Application number 6. Electric field intensity at a point closer to the charge conducting wire of linear charge density lambda and infinitely long wire. Right? Do this completely with step by step. We are going to give marks.